How you decide?
No, she just said pick a side.
Okay, that's wrong. You you actually pick the more complicated side, which is counterintuitive, but it's usually easier to make something complex into something simpler when you're working on these. So for example, the plus, it's harder to go from a plus to a product, so we would work on the left side here.
Okay.
Okay, and it's kind of counterintuitive. You can work on both sides, but it's not like solving. You can't move things around. You can't like divide both sides by secant x in this problem. Okay, so you just choose a side, choose it based on which one is harder or looks more complicated in general, and then you go from there.
Okay.
Okay, so the first strategy that you probably heard about in class is to write everything's in terms of sine and cosine. So tangent is sine x over cosine x, cotangent x is cosine x over sine x, and they get worse before they get better. So whenever you have fractions, you should say, oh, I need to make a common denominator. Okay, and that common denominator is to multiply top and bottom on the left by sine x, on the right top and bottom by cosine x. So it looks like this: sine x cosine x over, I'm sorry, I messed that up here. That's really bad. Okay, so we're going to multiply, this is sine squared x, because it's sine x and sine x, over sine x cosine x. Let me show that in blue in case you want to look back at this later. So you're multiplying the top and bottom by sine x, top and bottom by cosine x here. So in the numerator on the right, it becomes cosine squared x over sine x cosine x. And then you're supposed to say, oh, they're a common denominator. That's the whole point. I'm going to make it into one denominator. So sine squared x plus cosine squared x equal over sine x cosine x. Do you remember from your Pythagorean identities what sine squared x plus cosine squared x equals?
I do not.
Okay, so there's that really amazing cheat sheet. I'll throw in the chat. I'll also pull it up and pull from it today. Different identities that you need to know. There's so much here; it can be overwhelming. But this is one that you definitely want to have memorized for the test or quiz. So these are the Pythagorean identities. Whenever it's sine squared plus cosine squared, that's always 1. Okay, so the numerator becomes 1, which is nice. Okay, and sometimes it's good to bring down that right-hand side to kind of remember, like, what are we trying to make this even look like? Okay, it's secant x, cosecant x. And you can see we're not even close, but you might remember that secant is really the reciprocal of cosine, and cosecant is the reciprocal of sine. So you can actually write these as 1 over cosine x, 1 over sine x. One times 1 up top makes 1. And there you've got it. The cosine x, 1 over cosine x is the secant x, 1 over the sine x is the cosecant x, and you have it. And you say that you're done or something. Sometimes they're like, oh, QED. I actually don't even know what that means anymore. But the idea is you make the left side look like the right, or the right look like the left, and then you're done. You've got it. So you can skip some of these steps that we did here. Like I mean, you obviously don't have that much room on your paper to write all these down, but you need some amount of paper because you work vertically, never horizontally on these. Like you could go from the first line down to the second. You might be able to say, oh yeah, sine squared plus cosine squared is 1. So you can shorten this a little bit, but it's not great. I mean, there's a lot of stuff to do here. Questions on that?
No?
Okay, let's look at number 3 next. All right, which side looks more complicated to you?
The left side.
Yeah, so we're going to unfortunately work on the left side. Left side is the worst one. Just like in the previous problem, you generally want to make a common denominator. And you do that by multiplying by the other one. It just so happens to be the conjugate, which is helpful. You do use this technique of multiplying by the conjugate a lot in this class. So I'll write that here. You're going to do 1 plus sine x, 1 plus sine x, 1 minus sine x, 1 minus sine x. So like a problem like number 11, or even number 1, 11 is a better example. 11, we'll just do that one next rather than me starting to talk about it. Okay, so on top, you're going to have 1 plus sine x. Okay, and then on the bottom, it's really good if you remember how to FOIL something like this and see the cancellation. And if you don't, you got to FOIL it out. It's 1 plus sine x minus sine x minus sine squared x. But you can see that the outer and the inner terms, the O and the I, they cancel. These cancel right here. So on the bottom, you get 1 minus sine squared x. Minus, on the right here, 1 minus sine x. If you're wondering why I'm putting it in parentheses, it's because I haven't dealt with the negative sign yet, because we're going to probably end up distributing it in. On the bottom, though, you get the same thing as the bottom on the left, 1 minus sine squared x. Any questions on that so far?
No?
Okay. All right, so up top, it's 1 plus sine x, distribute that negative, minus 1 plus sine x, all over 1 minus sine squared x. So in the numerator, the ones cancel, and you're left with 2 sine x, and up top, 2 sine x over 1 minus sine squared x. But if you go back to those Pythagorean identities, do you remember what that reduces to, what 1 minus sine squared x reduces to? Yes, no, maybe.
I'm thinking.
Is that happening? Okay, so the idea here is if you solve it if you move over the sine squared x or theta, it becomes the other one. It's cosine squared x equals 1 minus sine squared x. So the 1 minus sine squared x is replaced by the cosine squared x.
Okay.
So in general, like when you see a sine squared or cosine squared, just like we saw in the last problem here, sine squared plus cosine squared, you're almost always going to use this top Pythagorean identity. Okay, now if you're wondering, well, why are we doing that? Again, like sometimes it's good to go back and be like, well, what are we actually trying to make the right-hand side look like? And we're trying to make the right-hand side look like a 2 tangent x secant x. We're like, oh, good, we got the 2. We got the 2 already. But how do you turn this mess into tangent secant? And it helps if you write them out without the squared. So it's cosine x, cosine x. Now, do you agree that that sine over cosine is tangent? Do you see that there?
Yeah.
So there's really like these 3 parts. There's the 2, sine over cosine, and then the 1 over cosine. And then we have all 3, because sine over cosine is tangent, 1 over cosine is secant x, and you bring the 2 down, and it's all done.
Okay.
So what about this seems difficult so far?
I think it's just me not knowing what equals tan and what gets to like the equations and
Okay.
stuff.
Are you comfortable though, like foiling? Are you comfortable with like making the common denominator? Because you're gonna do a lot of that.
Yeah.
Okay. There's like a lot of problems here. Like if you had a trigonometry textbook, I mean, there's like 2 pages of problems for these, and they're all in play. I think we learned your instructor doesn't always choose the problems like the ones you're doing. So not always the best. Okay, let's look at number 8. I guess we'll look at 8. I don't know, like we can work on any of them. I'm just sort of picking and then randomly, and then I figured around the 30-minute mark, we'll go solve some. Okay, these should kind of look equally complicated, but I would argue that the secants may be more complicated than the cosine, so we probably will work on that side of it.
Okay.
Does that sound reasonable?
Yeah.
Okay, so the very first strategy I mentioned is you always write things in terms of sine and cosine. So secant is really 1 over cosine x minus 1. Again, secant is 1 over cosine x plus 1. You may be saying, well, hey, didn't you say you always multiply by the conjugate? It's like, well, yeah, that does work, but in this problem, there's kind of a better way. And it comes from, again, just like having the right hand side. It's like, okay, because it's kind of almost there on the bottom. 1 plus cosine x, there's the 1, there's the cosine x. And sometimes, again, these are non-obvious, so you got to see them the first time. But if you multiply everything on the bottom by cosine x, okay, and everything on the top by cosine x, let's see what happens here. So you get in the top, you get sorry, let me put this in parentheses. In the numerator, you get cosine x over cosine x minus cosine x. On the bottom, you get the cosine x over the cosine x plus cosine x. And then the cosine x's cancel, making 1 on the top, 1 minus cosine x. And on the bottom, you also get the 1 plus the cosine x. And you have it. So occasionally, like there is a shortcut and you don't just multiply by the conjugate when you try to solve these. Did we do 7 yet?
I don't think so.
Yeah, I don't think so. I think we did either. I don't know. Is there one here you want us to do? I mean, you see that they get more and more difficult on the right-hand side. Are there ones that
Yeah.
maybe one that stands out to you like, oh boy, we better do that one. I have no idea how to do it.
Probably 17.
Okay. 17 is yeah. It's awful. What would be so it'd be really good like if you had like friends in the classes, if you guys worked on a bunch of these separately and then send each other the solutions, because it's just so much to work on
Yeah.
your own. Okay. In your opinion, which is the more complicated side, the left or the right?
The left.
Yeah, I would agree. Now, when I see squared, you normally think, oh, Pythagorean identity, but because there's 3 terms here, and you'll see this when we do the solving, is you might look at this as u squared plus 3u plus 2, and then you can actually factor this. Have you seen that Have you seen that before in class?
Yeah.
Maybe. Okay. So this factors into u plus 2 and u plus 1. And u is always this middle term without the coefficient. You did that in algebra 2 at some point, maybe even algebra 1. Okay, but the u is only to make it like more familiar to you. It's still cosine, so it's really cosine x plus 2, cosine x plus 1.
Hmm.
Okay. So we did all of that to make the bottom into, or the left side into, sine squared x over cosine x plus 2, cosine x plus 1. All right. Now, when you swim, do you do you look for the wall, or do you just know where it is, or how does that work? Is there some anticipation?
Um, you follow the black line on the bottom of the pool
So
until it,
you kind of know though when you're getting to the end, because doesn't the line run out, or is it run all the way up to the wall?
it runs out.
Okay. All right. So I guess what I was going towards here is like, you always want to keep in mind your target. You want to like, okay, I want this. What do I have? And you can see you actually have one piece of it already. You agree with that? Do you see that?
Yeah.
Okay. Now with the sine squared x, you want to always go back to the first Pythagorean identity. Sine squared x plus cosine squared x equals 1. So sine squared x, if you were to solve this for sine squared x, okay, that means subtracting the cosine squared x from both sides. You get sine squared x equals 1 minus cosine squared x. So instead of sine squared x, we're going to put 1 minus cosine squared x in the numerator.
Mm-hmm.
And then cosine x plus 2 in the bottom, cosine x plus 1 up top. And you can see we kind of have the 1 minus cosine x. We're really, really close. Okay. Any idea how to factor the numerator? It is,
Um,
sorry, go ahead.
oh yeah, it's the difference of squares.
Yes. Okay, so that, as a reminder, it's a squared minus b squared equals a minus b, a plus b. Okay, so basically you say to yourself, oh yeah, it's really 1 minus cosine x, 1 plus cosine x, because 1 squared is the 1, cosine squared is the cosine. So you write 1 minus cosine x, 1 plus the cosine x over cosine x plus 2, cosine x plus 1. And you're like, oh, I see something here I can cancel. And that's what you were looking for. You're looking for cancellations there. And then you've got it. Now you do have to show kind of that final line that's exactly like the one on the right. But it's not like geometry where you had to explain the proof. You know, you don't have to give a reason. You just have to show it. Show that it works.
Okay.
Now, keep in mind right now that all the ones we've worked so far, I've known the first step to take. So we've always been going in the direction of the solution. Sometimes you don't know the right step to take and you try something that does get worse before it gets better. So you may have to restart some of these. You know, if you get far enough in the problem, you're like, this isn't looking right. Yeah, I mean, you may find that that's not going to work. And some look really difficult, kind of like I won't say that, like this 8, you know, maybe like a problem like 8 we did where it's like, man, what do we even do? And it's actually pretty quick to do once you kind of know how to start the problem.
Okay.
Okay, we should spend a little bit more time on this before we go to the solving side. Unless you want to move to the solving side now, but what is there another problem that stands out? I mean, we've covered a lot of the strategies thus far.
Yeah. Probably number 12.
Okay, yeah, let's do it. So number
Okay.
12, is there anything to the right of the secant on number 12?
Plus cosecant x.
Okay, let me snip that in. So it's plus cosecant x here, like that.
Yep. Yeah.
Okay, which side is more complicated in your opinion?
Probably the left side.
Yes. So you're gonna foil the left-hand side. So that's sine x tangent x plus sine x cotangent x plus cosine x tangent x plus cosine x cotangent x. So generally you foil when you see something like that. Let me see if there's another one I can make a comment on. No, I guess there isn't. Problem 16, you factor. I'm sorry, 20. 20 is a foil one. Although it's got some other things going on. But yeah, you would foil 20 just like you do here. Then you'd write everything in terms of sine and cosine. So sine x over cosine x plus sine x cosine x over sine x cosine x sine x over cosine x plus cosine x cosine x over sine x. And this does help because you eliminate a few things that maybe you wouldn't have seen. The sines cancel, cosines cancel, like that.
Okay.
All right, so let me rewrite here. So we got sine squared x over cosine x plus cosine x over 1 plus sine x over 1 plus cosine squared x over sine squared x. Sine x, sorry, sine x. Okay, so it doesn't look great. Let me go back. We need this to look like secant x plus cosecant x, like that. So we're kind of making some way there. There's kind of like, you can see like 1 over cosecant x is the secant x, but really it's like, well, what do I even do next here? And this is why just seeing them a few times helps. Like I look at these two and I'm like, oh, if we make a common denominator of cosine, which means multiplying the top and bottom on the right here by cosine x, that's going to produce something really nice. Sine squared x over cosine x plus cosine squared x over cosine x. When the bottoms are the same, the top becomes sine squared x plus cosine squared x, and that becomes 1 in the numerator. That's the Pythagorean identity. But you kind of have to look ahead. You have to be like, well, if I multiply by cosine x, I get a common denominator, and then in the numerator, oh yeah, that's really 1. Sine squared x plus cosine squared x is 1. 1 over cosine x is secant x. And you realize like, oh, that's what I wanted. I wanted a secant x there.
Hmm.
And so if that works for the first two, you then know, okay, I probably should try the same thing for the next two. Except I'm gonna multiply the other one by sine x and sine x. And these are non-obvious. Like you would never know to do these until you've worked them a few times.
Okay.
So like anything else, the more you practice, the more you know what to do. You get the sine squared x plus cosine squared x again, which is 1 over sine x. 1 over sine x is cosecant x. And there you have it.
Okay.
There's a lot. It's a lot here. Like this is harder than, in some ways it's harder than the other things you've been doing in math, but in some ways it's like, well, you're just manipulating equations. It's like dealing with literal equations. It's not, you're not actually solving for anything. But you can see how much work there is to get through one of these potentially. All right, let's look at the other side of the page and work through some of these. I'm going to start with 13, which is kind of halfway down the middle of the page. Not sure why. It's the most basic one though, so we'll do that. Okay, so in general, when you're solving some sort of a trig function like this, you always want to isolate the sine, the cosine, tangent, the secant, the cosecant, and the cotangent. Like whatever it is, you want to isolate it. So here you're going to add 1 to cosine theta equals 1, divide by 2, cosine theta equals 1/2. Okay, and this is where you go to your unit circle, which is on that reference sheet I sent you. I think it's page 3. You go to your unit circle and you're like, all right, where is the x value? Where is the x value positive 1/2? And you're like, oh, there it is. There's one there and there's one there. And it really helps if you know your unit circle.
Yeah.
Do you know your unit circle?
Partially.
Good. Is there a plan to beg for the unit circle on the quiz or test?
Yeah.
Okay. I would keep asking. Sometimes they do give in with that. So do you have those angles for me? You got one going this way and then the one going all the way around. Can you tell me those?
Um, I'm gonna guess and say it's.
Well, that's okay. I don't want you to guess. Let me pull that reference sheet up. Yeah, it's in the chat. If you got another window you can get open, it would be good to have that up. But let me snip that in here. Problem is that I really need to snip the whole thing in, so it's not great, but that's okay. Here we go. We're going to down here. So you're looking at, again, where the x value is 1/2, that's here, pi over 3. And then down here, add 5 pi over 3. So those are your two answers. Pi over 3 and 5 pi over 3. And that's about as basic a problem as you could get because you don't have to do any really manipulation of anything. All right, so let's look at 22 next, unless there's some more questions about that one.
No.
Okay, so just like in the previous problem, you want to isolate that trig function. So you're going to divide both sides by 3. Tangent squared theta equals 1/3. You can take a square root of both sides. So it's plus or minus the square root of 1/3. So tangent of theta equals plus or minus the square root of 1 over the square root of 3, which is 1 over square root of 3, like that. And a couple of choices here. You probably should rationalize. So the plus or minus root 3 over 3. Okay, so now what you're looking for in the unit circle is the angle where the y over the x value is this number, the square root of 3/3. Okay, and it's not obvious because you'll notice that they don't give you the tangent value in this unit circle that I just grabbed in here. So you have to know a bit of information to be able to do this. You have to recognize that the square root of 3/3, is not on there. Like, you're not going to get that on there. So, well, how can you get it? Well, if you do 1/2 over square root of 3/2, okay, this reduces to 1 over the square root of 3. Okay, so you're looking where the x value is 1/2 and the y value is root 3/2. So like right here at pi/3, the x value is 1/2, the y value is root 3/2. It becomes 1 over root 3, which you saw earlier, and then that rationalizes to root 3/3. So this unit circle is super critical to know that, oh yeah, it's that one. And then it's also this 2 pi/3. And the reason is because we also allow for plus or minus. And then this one down here, again, it's got to be the right order. The x has to be 1/2, the y has to be root 3/3. So this 4 pi/3, you notice a pattern here with the over 3s, and then 5 pi/3, those there. So there are your 4 answers. So for me, like if I put this kind of a question on a test or a quiz, if you got down to like this line right here, you probably feel like you've done a lot of the work, but it's really only half, because you really need to know your unit circle. So I can't impress upon you enough how important that is to know for this class.
Okay.
I've never been asked for a unit circle value, but only in classrooms.
Okay.
Any questions on that, or anything unclear?
No?
All right, we're gonna look at 20. You choose 14 or 21. No, I'm sorry, that's wrong. We need to do 21. You kind of got one of each type here.
Okay.
Okay, so this is similar to one of the problems that we did earlier. I'm going to scroll up and show you that we did this kind of problem earlier. It's right here where we made this U substitution. Okay, and we do that to make it easier to factor. Okay, so like if you were to look at this as 2u squared minus u equals 3, and I asked you to solve it, you would remember at some point that if you subtract 3 from both sides, you can now factor this. Okay, I mean, there's a couple of ways to do it. We're just going to use the guess and check approach here. All right, and so you're trying to figure out, well, what do I multiply by 2u and by u by, so that I get -1 here in the middle? And the answers are, it's either -1 and 3 or 1 and -3. So if you're not sure, I'm going to help here, just for time here, time's sake. Make sure we get through as many problems as we can, but you have to figure out the factoring. So that's a skill that they assume you already know.
Okay.
Now, and then from here, you're used to like, okay, I just set each of these equal to 0. So set them both equal to 0, and you solve for u. So on the left here, you would add 3 and divide by 2, so u is 3/2. On the right here, u is -1. But you have to remember to back substitute. Okay, and what that means is, hey, like you made a substitution for u, which it was this middle term. It's always the middle term without the coefficient. So your u is really sine theta. So it's really sine theta equals 3/2. Sine theta equals -1. Let me know when you get it caught up here and we'll talk a little more about this.
Okay.
Okay, so we're gonna look at the equation on the left here. If you recall the graph of sine, it starts at the origin, goes up, comes down, goes down, and comes up, but it's bounded between 1 and -1. Where's 3/2 on this graph?
It's above 1.
Yeah. So do these ever intersect?
No.
No. So this one has no solution.
Okay.
On the right's the unit circle problem. It's like, where is the y value -1 on the unit circle? So if you look at the unit circle, it's only 1 on the kind of the extreme points.
Yeah.
So the y value is -1 down here, and that's at -3 pi. I'm sorry, +3 pi over 2. So this one actually only has one answer to it. Any questions on that?
No.
Okay. I know this is not exciting. I probably say that every lesson. Like, these are really dry. There's not a lot of things that I can say to like make this more interesting, but we'll look at number 16 next. It's kind of like the one we just did. It's got a little wrinkle to it that makes it slightly different. It's really bad when you mix sine and cosine, or like when in 23 you see cosecant and cotangent. It's really bad when you mix them. Like they're really hard to solve. Okay, so maybe there's a way to make a cosine squared into a sine. Okay, and that's where you've got those identities: sine squared x plus cosine squared x equals 1. So you can actually replace cosine squared x by solving this identity for cosine squared. So we got cosine squared x equals 1 minus sine squared x. So instead of cosine squared x, we're going to write 1 minus sine squared x plus sine x equals 1. And the idea here is that, okay, we've got just one trig function here. We can deal with that. All right, now, just like when you're solving anything with a squared, you usually get everything on one side of the equation. So to do that, I'm gonna move everything to the right. Okay, so when you subtract 1 from both sides, you realize, oh, that cancels, and you're like, wait, maybe I don't have to do that. Maybe there's something else here. So on the left side, we're gonna just rewrite it out of a different order. Sine x minus sine squared x equals 0, because when it's equal to 0, that's really the key. That if you notice in the previous problem here, we had it set equal to 0. You want to get these set equal to 0. All right, now if you're not sure what to do from here, you will factor. and they both have a sine x. So you factor out a sine x and you get sine x, 1 minus sine x equals 0. And the analogous problem is like, what if it's u times 1 minus u equals 0? It's like, well, what would you do in this case? Well, you still set both of these terms equal to 0. So you're going to do the same thing for your line, for your sine x line. You're going to set the first sine x equal to 0, and then 1 minus sine x equal to 0. So on the right here, this becomes 1 equals sine x, or sine x equals 1. So what you're looking for is where on the unit circle is the y value 0. On the left here, y value 0. On the right, y value of 1.
At 2 pi.
So the preference is for 0, not 2 pi.
Okay.
Yeah. So yeah, so it's 0. How about, is there any other places?
I don't see any.
Okay, it's also at pi. The y value is also 0 at pi because you're back on the x-axis.
Oh, yeah.
And then the y value of 1. I mean, sometimes I didn't do this, but sometimes you just write the ordered pairs. So I'll do that now. 1 0 0 1 minus 1 0 0 minus 1. Sometimes that helps too to see it. All right, so the y value of 1 is at pi over 2. Pi over 2. And your instructor expects all of these. Did your instructor happen to mention if 24 was a mistake? Because it's very different than all the other ones. It involves a change of period.
No.
Okay, I'm gonna not talk about that one and hope that you get that maybe in class, because it would almost require an entire lesson with period changes. So let's look at 23. Mentioned this one earlier. It's like really bad, really bad when it's two trig functions. But you're slowly seeing like, okay, what if I turn everything into sine and cosine? So cosecant is 1 over sine x, and cotangent is cosine x over sine x. And that's good because now you can make a common denominator. 1 plus cosine x over sine x equals 1. So the next thing to do here is to multiply both sides by the sine x. So it's 1 plus cosine x. Does that equal sine x?
Oh.
And this one's a little weird. So I'm gonna graph this because it's sometimes you see the things by looking at the graph better to get an idea of what is going on here. And let me just get the period here. Just give me a moment here to get this snipped in. Actually, yeah, we'll do it that way. Okay. You can do this without the graph, but I want you to see what's going on here. So the blue is the 1 plus cosine x, and then the sine is the green. And you see that they intersect in two places. This other point is pi comma 0. And so the question is, well, how would you know to go about doing this if you don't have the graphs? Well, you can see since the answers are on the nice points, and these tend to be the only solutions to problems like this, is that you check those places on the unit circle. Okay, you check at 0. At 0, cosine, wow, way off today. Cosine is 1 and sine is 0. So 1 plus 1 is 2. That does not work. And you see that here, they're way too far apart. And then you check it at the other one. Okay, 0, comma 1. You're like, okay, cosine is 0, 1 plus 0 is 1, sine is 1. Oh, that works. We can see that there. Similarly, you come over to this other place at pi minus 1, 0. You're like, all right, cosine is minus 1, 1 plus minus 1 is 0, sine is 0. They work. Go down to this last place, 0, negative 1. Cosine is 0, 1 plus 0 is 0, sine is negative 1. They don't work. Okay. At the other places, what you will notice is that they're kind of continually getting closer, but not close enough or far away. These tend to only be solved on these nice points of the unit circle. So these are tough. I think these are tougher than any of the others because the other ones you can always break them down into like an algebraic problem. This is more like 1 plus y equals x. You're like, how does that even work? It's not really a perfect analogy, but it's kind of the right right track there.
Okay.
All right. I'm gonna just stop the recording here.